Hi, my name is Petra Bevandic, and I will be presenting our paper on automatic universal taxonomies for multi-domain semantic segmentation. Standard semantic segmentation takes an image and classifies each pixel according to a predefined taxonomy. Here we see an example of an image segmented according to the cityscapes taxonomy. Simple segmentation models are usually trained using the negative log likelihood loss, which teaches the model to output the correct ground truth class. The assumption is that the model outputs prediction into a flat set of classes, which corresponds to the dataset taxonomy used to label the training images. The multi-domain setup is more challenging because datasets are labeled according to their individual dataset-specific taxonomies. This means that we do not have a fixed taxonomy that was used to label all images and thus do not know the set of classes that our model should output. Furthermore, different taxonomies may not be compatible with one another, so we will have to find a way to resolve these inconsistencies between datasets. Labeling incompatibilities come in two flavors that we will demonstrate on the images below. Discrepant granularities occur when a single class from one dataset corresponds to multiple classes from another dataset. Below, we see that 8020K and Viper group all driving surfaces into a single class called road, while Vistas divides them into separate classes such as road proper, road marking, road crossing, and so on. Overlapping labels occur when a visual concept gets inconsistently grouped across datasets. Below, we see an example of pickups that get labeled as vans, trucks, or cars, depending on the dataset. In our previous work, we proposed to solve the problem of incompatible taxonomies with a universal taxonomy whose classes represent distinct visual concepts found in a dataset collection. Dataset-specific classes can then be defined as unions of universal classes, and their posterior probabilities can be expressed as sums of posterior probabilities of universal classes. This setup allows us to have a model which outputs predictions according to the universal taxonomy that can be trained in a weakly supervised manner using dataset-specific ground truths without additional relabeling work. Previously, we constructed the universal taxonomy manually. We extend our previous work to construct the universal taxonomy in a fully automated fashion. First, we will demonstrate how to construct a universal taxonomy for a pair of datasets. To do this, we will have to discover relations between classes. Notice that we can represent dataset relations with a bipartite graph. We next note that each connection represents a distinct shared visual concept. We can collect the identified visual concepts, that is to say edges and non-related classes, into a universal taxonomy and simultaneously define the mapping function. To discover dataset relations, we will rely on visual similarity, which we will determine based on co-occurrence statistics between ground truth labels and foreign segmentation model predictions. For each ground truth class, we will identify the most common foreign prediction and use it to construct a bipartite graph of potential relations. We can further introduce an interpretation to the most common prediction and hypothesize that the ground truth class is a potential subset of its most common prediction. This turns out relations graph into a directed bipartite graph. What happens now is that we may have contradictions. More specifically, chain suggests a subset-superset relation between classes from the same dataset, which would not be possible and will need to be resolved. To introduce our approach to conflict resolution, we will have to look at an alternative approach to multi-dataset training called naive concatenation. This particular approach treats dataset-specific labels as unrelated and can thus be trained using the standard negative log likelihood loss. The problem with this approach is that the same visual concept may be represented with multiple output classes. This may hurt evaluation, where we expect the correct dataset-specific subset of the output to win, but what happens instead is that the considered visual concept is recognized within a foreign subset of the output. We may improve the performance by introducing relation information into the inference procedure. In that case, we do not segment the image according to the posterior probability of output classes, but rather a score which we get by summing the posterior probabilities of the dataset-specific class and its related classes. In essence, this score allows us to see which visual concept won rather than looking at which dataset-specific output won. An added benefit of the naive concatenation baseline is that we can use it to extract co-occurrence statistics by treating dataset-specific subsets of labels as standalone models. After this detour into naive concatenation, we return to universal taxonomy construction and look at conflict resolution in a directed bipartite graph. To resolve conflicts, we will split our chains into pairs of conflicting hypotheses and use improved naive concatenation evaluation to choose a better hypothesis from each pair. After we have resolved the conflicts, we can construct the universal taxonomy. If we want to find the universal taxonomy for more than 2 datasets, we can perform pairwise merges iteratively until we cover all datasets in a given dataset collection. Notice that we do not have a ground truth available after the first merge, which means that we will have to replace ground truth labels with pseudo labels. That is to say, we will replace co-occurrence statistics with coincidence statistics. We next look at our experiments, which we performed on dataset collections which varied in size and scope. We compared our automatic universal taxonomies to the naive concatenation baseline, as well as manually constructed universal taxonomies. We used the efficient pyramidal SysNet model with a resonating backbone. Note that we use evaluation with the void class in our experiments, since these models may produce foreign predictions. Overall, our results show that we are competitive with the manual universal taxonomy and outperform the baseline. The knowledge of our final models exceeds the information that is present in each individual dataset. Universal predictions can be returned to the dataset label space for evaluation. Our approach produces less void predictions than the naive concatenation model, since it does not have multiple output classes responsible for the same visual concept. Furthermore, we are able to find some visual relations that we did not consider initially, such as subset-superset relations between tie and person seen in this example. We will now look at more detailed results. We first consider automatic universal taxonomy for a pair of datasets, that in this case, 8020K and Vistas. Our approach outperforms the baseline and reduces the number of training classes. We are also competitive with the manual universal taxonomy. We show that coincidence statistics can be used instead of co-occurrence statistics. We further show that co-occurrence statistics collected with separate models produce worse hypothesized relations than those collected with the naive concatenation model. Next, we look at our experiments on the MSEC dataset collection. The advantage over the naive concatenation baseline is more pronounced, as is the reduction in the number of training classes. Our approach performs similarly to the manual universal taxonomy, though it identifies less classes. We also see the advantage of our approach with respect to the MSEC approach of manually relabeling the dataset according to a fixed taxonomy, which omits some of the evaluation classes to contain this relabeling effort. To conclude, we show that it is possible to construct interpretable universal taxonomies in a fully automated fashion. Our approach outperforms the naive concatenation baseline, performs comparably to the manually designed universal taxonomies, and presents a more fully flexible approach than manually relabeling dataset collections. Future work should consider streamlining the proposed procedure, consider alternative approaches to hypothesizing relations between datasets, and looking into non-iterative approaches to universal taxonomy construction. This work has been sponsored by Croatian Science Foundation and the European Regional Development Fund. We thank VSite College for providing us with access to 6 Tesla GPUs. You can find more details in our paper. Thank you for your attention.